All right, good afternoon. So it's 3 o'clock, so I'll begin. So thank you everybody for coming. My name is Ernest Ryu. I'm a new faculty, tenure track faculty in the mathematics department, specifically the applied group. Today I'll talk about say a few things about large language models.
Maybe you can dim the lights a bit.
Oh yes. Let's see. Yeah, I suppose it's better to do it right. He's pulling a little bit. Oh, all right. All right, so but before I get on with the material of this talk, I'll just do a very quick introduction of myself. So again, I'm a new faculty here in this department, I have three main research interests, and it's described in this Venn diagram. And today's talk will span so 2 out of 3 subjects, namely machine learning theory and empirical deep learning. If you are for the students, if you're interested in hearing about my optimization set of research, there is I'll be giving a talk at Guido's optimization course as a guest lecture. So, okay, so let me begin, and I'll first talk about how amazing large language models are. So how do you train? Well, really train a large language model. So step number 1, you first get internet scale huge data. So you try to get all books, all papers, all archived papers, news articles, everything ever written by a human being, written down in electronic form. You try to get it. And then step 2, you train a transformer architecture via next token prediction. So what is meant by next token prediction is you show the neural network architecture, the first part of the paragraph, the sentence, your text, and then you ask the transformer your neural network to predict what's going to come next in terms of the next word. And this is a very simple objective, but in order to be able to read a paragraph and then predict the next word, the model really needs to understand language very well, and it also needs to understand our world very well. So, for example, if there's a sentence, Charlie was very tired during his studies, so he went to Starbucks to get a cup of something. Well, then we all know that Charlie was trying to get a cup of coffee because we have world knowledge. It's not a matter of just knowing language and grammar. You need to acquire good world knowledge to be able to perform this next token prediction task. So this step 2 is the massive scale training that happens in terms of computational costs. Think of step 2 as costing tens and even hundreds of millions of dollars. And then step 3, there are a few additional things which I won't talk about. These are generally referred to as instruction fine-tuning, reinforcement learning with human feedback alignment, but I won't talk about that. That's not subject of today's talk, so I'll skip over that. And then step number 4 is, now that you have this finished, polished, aligned large language model, we use it for a downstream task. So whatever it is that you want to use a large language model for, you can just use it as is, or you can further fine-tune it to induce certain behaviors for the application at hand and use it. So my view is that LLMs are so powerful that they're really taking over really almost not in the entirety, but so much of machine learning. So I'll show you, I'll give you an example to convince you that really LLMs have this sort of outsized sort of impact. So okay, so in the reinforcement learning literature, people have for a while studied algorithms that can play video games very well. And it's a nice test bed because video games are closed environments. They're very cheap to emulate. So in the classical game called Montezuma's Revenge, which is an Atari video game, you're controlling this human with a hat, a cowboy hat, and I think this game is meant to be inspired by Indiana Jones. in any case, you're sort of going through these dungeons and exploring things. And within this game, there's this part where you have to pick up this key thing, and you hold on to it. And later, when a keyhole appears, you insert the key into the keyhole, and then you progress to the next stage. Now, if you just train a naive RL agent, then it can be pretty good at breaking bricks and doing other, shooting lasers at aliens. It can do those things pretty well. But something like this is very difficult for the classical RL agents because they do not have world knowledge. And here, the shape of this object is, well, humans recognize it as a key, and we understand that key is a useful thing that you may not immediately use. And then later, when you see a keyhole, you understand that, okay, well, the key is compatible with the key. We understand that, but classical RL agents do not. But how do we play? So here's an idea of how to resolve this issue. What we do is, first we remember that in the 70s and 80s, here's what video games look like in the store. You purchase a box, and you open the box, and here's a game cartridge, which you would insert into the console to start playing the game. But there's also this instruction manual. And you would flip through these instruction manual because it would really stimulate your imagination, and it tells you how to play the video game. And and it also explains what these square boxes are. The square box is meant to represent an alien. Okay, so then that helps you imagine things. And this is what they look like. You open it, and they're pretty pictures, and also a lot of very detailed text. So here's how we can solve Montezuma's Revenge and many of these Atari video games using large language models. So it's very simple. First, you scan the instruction manual and feed it into ChatGPT. Let the LLM read the instruction manual. And then step number 2, you write the simple script that translates the visual information in the video game into text. And then you feed this, 2-3 sentence paragraph into the large language model at every moment, and have the large language model dictate what we should do. So if the LLM, based on its information, prior information from the instruction manual, and based on the visual information described in text, if it tells us to move north, well, we move north. And this works very, very well. Yes.
Are they also fed with visual information from the instruction manual? Because we're also using pictures when we do that in the first place before we even start playing the game. Is that also part of the training?
So in this research, so here I'll clarify that there is no training aside from the ChatGPT being trained by OpenAI.
But this is also, there's still visual information before the game starts and training. Is that?
So in this research, all visual information in the instruction manual is not included. It's discarded.
Okay.
So there is some human intervention in the sense that the human writes the script, converting the video game screen into a text description. But that's the only thing human does. Okay. All right. And here's another sort of work in a similar kind of vein. So this is work that I participated in. It's entitled Image Clustering, Image and Text Criteria, published this year. So large language models, and around the time that, around mid last year, ChatGPT and a lot of language models basically acquired eyes. And these are called multimodal large language models. And basically you imbue these LLMs with vision capabilities. And now you can provide an image and then talk about the image in the large language model. So this is a kind of funny, unusual picture because at the back of the taxi, there's this person ironing his shirt. It's weird. And if you ask the LLM about it, it understands that it's weird for that reason. Image clustering is a quintessential classical unsupervised learning task. What is the task? Well, you provide the algorithm with a bunch of images, and you just group them together based off of which is you make groups of clusters of similar images. Now, but if you think about this task, it's actually fundamentally very ill-posed, because what do you mean similar, right? And this is I guess is meant to be a successful depiction of image clustering, and I guess similar color palettes are grouped together, but It's ill-posed. Unless you tell the algorithm what you mean by similar, unless you provide some sort of description about the metric in terms of that defines the distance between images, it's an ill-posed problem. So image clustering classical image clustering is ill-posed because the criterion by which you want the clustering to happen is not specified. So then what we did is here's a result of what we did. We have the user specify the clustering criterion in natural language. So these 3 rows, it represents the same data set clustered in 3 different ways. In the first row, the user specifies the criterion to be just the location. And then it clusters the images based off the location of the activity. So restaurant, educational institute, store, sports facilities. Those are the clusters that arose from this clustering algorithm. The second row, the user specifies the criterion mood. So joyful, adventurous, focused, relaxed. Third row is action. So blowing bubbles, applauding, jumping, shooting an arrow. And with this, we really we have a more direct control of the kind of clustering that happens. And also, by being specific about how we want the clustering to happen, we can significantly outperform traditional deep clustering methods. And at a high level, here's how we did it. We basically we take our images, right? So this is an image clustering problem. So the input is just a collection of images. In step 1, we provide a collection of images, and we use a multimodal large language model to convert these images into n paragraphs. Each paragraph is describing the corresponding image in a way that's relevant to the user-specified text criterion. And then in step number 2 and step number 3, basically we tell ChatGPT cluster these paragraphs, and then that's it. Yes, of course.
How your production slide? How do you make sure that the joyful adventure, those things are not super detailed? Like joyful wearing a blue t-shirt, like, and you get clusters with one image.
So one thing that I omitted is basically every single clustering algorithm out there, including ours, requires a user to also specify the number of clusters. So in this clustering result, the user specified the text criterion and the number of clusters being formed.
There are algorithms that don't specify.
So I guess that I was a bit, it was a bit of a hyperbole to say that all of them do require, but many of them do. And having to require the cluster count is a feature. It's a hyperparameter. It's a drawback of this approach. Okay, so my conclusion to this first part is that LLMs are really they're very, very, very powerful. So much so that a lot of recent research has been focused on reducing non-language tasks into a language task and have LLMs solve it. And I told you about this RL video game playing agent, and this it really annoys a lot of classical RL researchers because they don't think of using an LLM as RL, but it is. But they have their benchmarks, and using LLMs, the LLM beats the benchmark, beats the classical RL algorithms in those benchmarks. So LLMs are clearly engineering marvels, and there's been a lot of engineering research on how to build LLMs, how to improve LLMs, how to fix some deficiencies of LLMs, and also finding new uses of LLMs. And this has been very fruitful, as we all have seen. But then I want to move on to the question. The main focus of this talk is to address the question of why do LLMs work so well? And LLMs, I've been very positive about their success, and they often do work very well, but sometimes they do fail miserably. So it works well, it's impressive, and at the same time it does very silly things. It's hard to sort of square this. So it would be good if we can have a more fundamental, more principled understanding, or even more principled methodology for trying to get to a more principled understanding. So in this talk, I'll present one mathematical analysis and one scientific analysis of large language models. Right, so first, in part two, I'll talk about a math approach. But before I do so, I'll clarify a recent paradigm shift in machine learning, and that is the use of foundation models and fine tuning. So in classical machine learning, which I'll say, so in my mind, classical machine learning is in the 2010s, and it can involve deep neural networks, things like ResNet. But the idea was to you first specify and identify the task that you want to solve. So maybe you want to distinguish spam emails from non-spam emails. You want to distinguish a cat image from a dog image. You identify a task. Then you collect the data, that labeled data that indicates indicates the correct answers to these tasks, and then you train a specific model. You set up a logistic regression, a deep neural network, something you train based on the data. Under this paradigm, let's say you have a spam filter. You would not expect your spam filter to be able to plan your summer vacation to Paris. That seems like a very that feels very weird. That's not what this is meant. A spam filter is designed and trained to filter spam. But in the 2020s, now we're in the era of foundation models. So the first step of this paradigm is to have someone, probably not ourselves, at least not myself, have somebody train large foundation models, and these foundation models will acquire general knowledge and reasoning capabilities, and the cost of doing so will be in the at least $1 million. Now, under this paradigm, let's say you are interested in building a translation machine. So, and specifically, let's say English to Spanish translation. That's the only thing you care about. You care about nothing else. Nevertheless, the best approach, the state-of-the-art approach, is to train a generalist LLM that reads math, reads your math archive papers, goes into Reddit and looks at all of that. You train a generalist LLM that can do everything. And incidentally, it could also serve as a spam filter if that's what you want to use it for. And unlike human beings who have a finite time on Earth, the training time of these large language models, they're really only capped by the amount of capital that the companies can spend. So generalist models outperform specialist models by a large margin. So once you train a large generalist model, then you can fine tune on small specialized data sets to elicit certain behavior. And this can be very fast. So even if you take an open source large language model, something like Llama, which costs millions of dollars to train, if I want to do an academic research by fine tuning it, I can do so on a single, let's say a $500 GPU on my desktop. So that is to say that fine tuning has become a crucial component of the modern deep learning paradigm. And I want to introduce a work that I've done, that I published this year. It's called the LoRA training in the NTK region has no spurious local minima. So what is LoRA? So LoRA is the abbreviation of low rank adaptation. And what it does is it fine-tunes a large pre-trained language model by introducing low rank updates to the attention layers. So the attention layer of the transformer has a lot of components, but within the attention layer, there is a linear mapping. So X gets mapped to W times X, where W is a matrix. And what I mean by a low rank update is instead of, so imagine W is a D by D matrix. Instead of changing the entries of W, all these squared entries of W's, what we'll do is we'll keep W frozen, and we'll replace the linear operator, the matrix, with W plus B times A. B times A is a rank R product. So B is a tall matrix, and it's a skinny matrix, and A is a flat matrix. So that it's only rank R, and you have much fewer parameters than D squared in B and A. The weights W are acquired through the expensive pre-training process. And then after that, it's frozen and they're not updated, while the low rank factorizations A and B are trained during the fine-tuning process. The reason LoRA is used is because it's primarily used to reduce memory cost. So in a $500 GPU, you would have the GPU memory would be something like 32 gigabytes, and you would want your LLM fine-tuning operation to fit in that 32 gigabytes of memory. So if you want to take an open source large language model and fine tune it on an academic GPU, where the bottleneck is usually in the memory, then the use of LoRA coupled with some sort of quantization techniques is mandatory. So everybody who does LLM research from an empirical angle, everybody uses LoRA. Literally everybody uses LoRA. So the LoRA, the 2022, the idea of LoRA was published, and as of today, it has more than 7,300 citations. So the prevalence of LoRA really warrants theoretical research. But there has only been a handful of papers that really analyze the behavior, the training dynamics, or the statistical guarantees, the effectiveness of LoRA in a theoretical way. So that is to say that this is, I think, a fertile area where a lot of high impact and interesting theoretical research can happen. So let me kind of go through the problem setup, and I'll go through it quickly. And if you're sort of unfamiliar with your transformer architecture, maybe you won't follow every single bit, but I'll try my best. So we start with a transformer network, and the transformer network has a lot of weights, and we won't fine tune all the weights. We'll only fine tune a subset of weights. So this set of W weights, that's the set of weights that we will fine tune. And these are the linear operators in the attention layers. So all these W's are matrices. And there are going to be many matrices within your neural network architecture, capital T in total. Now, for the sake of notational simplicity, I'll just say that T is equal to 1. So there's only one matrix in the entire network that we're fine-tuning. In the actual paper, we can fine-tune as many matrices as we want, but the notation, because we need to carry on around more indices if we want to do that. So there's going to be a pre-trained weight, a W0. We're going to use a fine-tuning data to do fine-tuning. Now, fine-tuning data, depending on the context, it actually can be quite small. So actually, it's not unusual to take a pre-trained large language model and fine-tune it on, let's say, 1,000 data points, because sometimes fine-tuning is a matter of personalization. So maybe there's some text that you wrote yourself, and you want to customize the language model to your particular behavior, in which case the data set will be actually very small. So think of n, the number of fine-tuning data points, to be something less than 1,000. The update that's going to happen is going to be denoted as delta. So W0, that's the pre-trained weight, and we'll update it to W0 plus delta. Okay, and the other idea is that, of course, delta is kind of small. So, okay, and then L is going to be a mean square error or cross entropy loss, some sort of loss that's convex and twice differential. Mm-hmm. Okay, so in the usual full fine-tuning setup, where we do not use the low rank parameterization, we are considering the loss. This is a fine-tuning loss. We'll update the model weights from W0 to W0 plus delta. But in lower fine-tuning, what we do is, instead of updating all the weights with this delta movement, we're going to parameterize delta with a low-ranked factorization. Delta will be written as U times V transpose, where U and V are rank bar factors, and that's going to be our update. And we'll directly, using gradient descent, optimize for U and V. In this work where we perform actually prove theorems, we make one crucial assumption, and this is in the deep learning literature sometimes referred to as the MTK assumption, but it really is just a matter of doing a first order Taylor expansion. So this is just a first order Taylor expansion with respect to the neural network parameters, not with respect to the input, because the input is text, and you wouldn't want to. It doesn't make sense to do a Taylor expansion with respect to text, but we can do Taylor expansion with respect to the parameters. So our assumption in this work is that the first order Taylor expansion is sufficient, and the second order terms do not really contribute. Now, is this claim true? It's the claim that the second order terms are not important is something that we do not attempt to analyze mathematically or theoretically, and I have no idea how to justify that mathematically or theoretically. But the fact that this delta is indeed small and that the first order Taylor expansion is sufficient is something that has empirical evidence from prior work. So here's a citation in particular. So people have have looked into whether this is a valid approximation, and in a lot of, but not all, but in many large language model fine-tuning settings, this is indeed a valid assumption. So it's something that I'll just assume before the proof of the theorem starts. So with this assumption, then we'll, instead of consider fine-tuning the full neural network, we'll consider fine-tuning the linearized version of the neural network. Okay, so with that assumption in, then here's the first result of this fine-tuning, of analyzing the fine-tuning mechanism. So, okay, so first of all, before using any low-rank parameterization, we consider doing full fine-tuning. We imagine we're allowed to fine-tune all the weights, all of the dense weights. And then the question is, if we were allowed to do so, is there a global minimizer of the fine-tuning loss that is low rank? Because before we decide to use a low rank parameterization, the question perhaps should be, is that a good idea? Will a low rank solution exist? And the answer is yes. So a solution, a global minimizer with rank on the order of square root of n is guaranteed to exist. Okay, so a low rank solution, a low rank global minimizer exists. So therefore, we can explicitly parameterize to search only for low rank solutions. So that justifies the use of LoRA. Okay, so we have existence, but then is it computable? That's the next question. Can we find this low rank solution using stochastic gradient descent, the algorithm that everybody uses? So let me quickly cover some background. So here's some terminology in terms of optimization loss landscapes. So when imagine L hat is a thing that we want to minimize, a function that we want to minimize, and we assume that it's smooth. Then we say a point U is a first order stationary point if the gradient vanishes. But if gradient being equal to 0, of course, doesn't mean we're at a minimum, right? So we could have saddle points. So next, we say U is a second order stationary point if it has vanishing gradient, and furthermore, locally the Hessian has no negative eigenvalues. So second order stationary point doesn't exactly mean it's a local minimum, but you roughly say so. You can roughly think so. Now, a strict saddle point is we say use a strict saddle point if it is a first order but not a stationary point, but not a second order stationary point. And here we have a visualization of a strict saddle point. Now, let's sort of try to imagine starting at some point in this loss landscape and trying to go down. Imagine running gradient descent or stochastic gradient descent on this loss landscape. Then it's pretty intuitively clear that the probability that you'll get stuck at this saddle point is 0, right? So in some loose sense, almost surely you'll never get stuck in a saddle point. So SGD and gradient descent will make the function value go down. It's not going to get stuck at a strict saddle point. So it might converge to a global minimum, or it might converge to a local minimum. So if SGD converges, then and there's some prior work that makes my handling the argument in a more mathematically rigorous sense. So if SGD converges, it will converge. It cannot converge to a saddle point. It will converge to a second order stationary point. Now, in general, second order stationary points may be very bad because you could have this very bad local minimum.
Very nice.
Yes.
In principle, with a saddle, it would be possible to get very, very close because maybe the negative eigenvalue, the negative part, is small. So it could take a long time before it escapes.
Yes.
And that might be something that happens in practice for computation. Are there any sort of assurance?
I'll actually.
We'll get to that.
I'll mention that, but to give you the answer, getting close to the saddle point and yes, escaping it in infinite time, but wasting a lot of time near a saddle point can happen.
Okay.
And the results that I prove do not address that at all. So that's still a
Okay.
possibility.
Thank you.
But so yeah, so but putting aside the speed of convergence, the escape time for the moment, if you just talk about escaping the saddle point or not, we'll escape the saddle point with probability 1. So gradient descent is going to converge to second order stationary points. Second order stationary points can be they can be bad. They can be very bad local minimum. But if we can show that all second order stationary points are global minimum, then SGD will converge to a global minimum. So here's the trainability result when it comes to LoRA fine-tuning. So what we do is we assume that a global minimizer exists, and we assume that the parameterization is the rank parameterization of the network is sufficiently larger than square root of n, and to make a sort of and then we take the loss function and we apply a small perturbation. So the technicalities of the proof is that if we do not apply the small perturbation, I don't know how to prove this result. But adding the perturbation is a way for us to say that this desirable property happens generically. And yeah, so this perturbation can be arbitrarily small as long as its density is smooth with respect to the absolutely continuous with respect to the bank measure. Then all second order stationary points of this training loss are global minimizers. So the conclusion of this theorem is that generically speaking, LoRA training has no spurious local minima. A spurious local minima would be a local minima that's not a global minima. It's the local minima that you don't want to get stuck in, and generically that's not going to happen. So this loss function, they're going to have saddle points, but SGD won't converge to such saddle points. SGD will converge to the second order stationary points, and according to this theorem, generically, those will all be the global minimizers. Yes?
So are you still talking about all of this in the kernel regime?
This is all in the kernel regime.
So like, okay, so like what's wrong with just saying that, okay, it's the same thing as kernel interruption, so it's a convex problem?
It's not a convex problem because it's in a kernel regime, but here, let's see. So it will be convex as a function of delta, but delta is then parameterized low rank. It's a low rank parameterization, so u times v. So then in the uv variables, it becomes not convex. So if you use actually the square loss, then you would get a not a quadratic, but quartic expression, and it will be non-convex.
Oh, I see. Okay. And also, okay, so is this also like, are you doing anything else with the network with like the activation functions for? Because I guess like if it's like not smooth, you could like.
Oh, so we're basically assuming everything is smooth, and I guess a lot of the activation functions that we use nowadays are actually smooth because people instead of ReLU, people use the GayLU and those things. Okay, and I'll just quickly mention that in this work, we also touch upon the issue of generalization. So under certain very strong assumptions, we're able to do a Rademacher complexity argument to show that the minimizer that we found through LoRA fine tuning is going to generalize well. Okay, so in this work, we provide a trainability and generalization guarantee for this parameter efficient fine tuning method called LoRA. There are some limitations to this. So in practice, when people do LoRA fine tuning, instead of using square root of n as their rank parameterization, people just use 4 or 8. That's just the rule of thumb. So I said that the number of data points n should be thought of as something like 1,000. Square root of 1,000 is 33. So the guarantee is, in my mind, not vacuous. It's saying that the rank should be bigger than rank parameterization should be bigger than 33. That I think that's okay, but in practice, people use 4. So our theory doesn't apply. And also, I said there's a lot of experimental justification behind the linearization assumption, but there's also some settings where it's clearly this linearization assumption is violated. So if so, then the theory doesn't apply. And also, there's no guarantee, so coming back to Mason's point, our result theorem 2 implies that the training will converge to the global minimum. It says nothing about how fast it may converge. And in the worst case, it can be pretty bad. So that would also be an interesting direction of future work. Any questions? Yes.
It's kind of a silly question, about the MTK assumption.
Mhm.
If your activation functions are smooth, I guess I'm just not seeing why you wouldn't kind of be able to get the MTK assumption for sure.
So the NPK assumption is that throughout the entirety of training, so initially delta is 0 because that's the definition, right? Delta is the perturbation. So initially the perturbation is 0, but as fine tuning progresses, maybe training needs to move a long distance, and then once it moves a long distance, it might move away from the region in which the Taylor expansion is good. Okay. Any other questions? All right, next, part 3, I'll talk about a scientific approach to analyzing large language models. Okay, so let me first tell you about the in-context learning. So in-context learning, which I'll abbreviate as ICL, this was a capability of large language models that was first reported with GPT-3. So models prior to GPT-3 didn't really have the ICL capability, or when it did, GPT-2 kind of had it, but it was very weak. But so it's something that emerged at a certain scale. And with ICL, the model is able to do tasks that are implied by the context of demonstrations without an explicit description. So if you tell the language model to please translate this paragraph into Spanish, that's not in context learning because you describe the task that you wanted to carry out. But in context learning, you just show some examples and the model figures out what you mean. So here's an example of just standard non-ICL, just next word prediction. Just you have a prompt and then it'll just do the completion. But in context learning, here well, rose, red, sunflower, yellow. Well, we understand, right? It's picking up the color of the flower. And ICL also works with very arbitrary rules. So here, yeah, you take X, Y, and then the next thing you repeat it twice. You just delete you don't use this @ symbol, and then that's the completion, right? So for us humans, it's easy to identify what are the rules being demonstrated, and GPT-3, GPT-4 can do this very well.
Can I ask about the second example? Because I actually didn't know that lavender was a flower, so I also had to infer that lavender was a flower. And in that context where you have a word that means multiple things, how is ICL working in that case? Does it have to do one inference and then do the second inference? That's what I had to do.
Well, it's so I think your answer, your question may be a little bit too specific, because the general observation is that language models are very good at doing whatever inference it needs to do. So it can do it, but it's hard to break down whether it's doing it it's hard to know whether it's doing it in a step-by-step manner.
Right, but the point is there's an ambiguity if a word has two meanings.
Yes, so this is an example that I actually did this on ChatGPT, and it
Okay, so
worked.
it's better than, I had trouble, so.
Well,
So apparently humans are not always good.
I think with a few more examples, I think you'll be very sort of convinced on this ability. Okay. All right. So I don't actually speak or read Spanish, but with the help of Google Translate, I made this example. This is something that I just tried actually yesterday. So here's a prompt. This is what I wrote: complete implication. So banana, bonanza, car, and that, and grass. Okay. So for those of you who speak Spanish, you might think this is a little bit weird, because this is not the translation of those words, right? So here's what ChatGPT outputs. It says T. So T in Spanish is T. So that's a Spanish word. And it realizes that, well, it's this weird thing where I'm not doing a translation, but I'm taking banana and getting a similar kind of thing, in this case, apple, and then doing the Spanish translation of that. It picks out this rule perfectly. And so now the answer that should go into here is not deterministic. I mean, it could be T, but it could be, if it chose Coca-Cola, I think that'd be fine. But I think this is a perfect answer. Yes?
Just so you know, T is not the word for tea in Spanish.
Oh, it's not. Okay.
It's just T and E without the A.
Oh, so they got it wrong.
Yes.
Okay. So it did get it wrong. Okay. All right. So, but I think my point still stands. That in that it's very good at sort of understanding sort of the context, and through the demonstration, it perfectly understood what I was trying to do with these examples. Okay, so now let's consider a more stylized, a more controlled sort of example. Okay, so here are a bunch of implications. All right, so now in the interest of time, I'm not going to have you think about this for 5 minutes and then figure it out. But here is the idea that this is the product. Okay, so you have these vectors that match to some plus minus number. These are Boolean vectors, right? And then the question is, I would ask ChatGPT, what comes next? And actually, here what's being demonstrated here is a sparse parity function. A sparse parity function takes it as input a Boolean vector, selects a sparse subset of indices, in this case, index 3 and 4, and multiplies them or computes the XOR of them. Okay, so once you identify these the support coordinates, then now you can do the computation and answer provide the answer. And my claim is that, and this is not just my claim. What can be demonstrated is that ICL is algorithmic reasoning. Okay, so ICL, when this capability was first observed around in the year 2022, people initially thought of ICL as just a prompting technique that merely specifies the input-output formats. But nowadays, people's perspective has changed. So now we understand through a lot of these controlled experiments that the transformer, the language model, must be internally implementing an algorithm to be able to perform in context learning. So let's say we have a priori knowledge that a demonstration that looks like this is a demonstration of a sparse parity function. So f is some sparse parity function. X is a Boolean vector. F is a sparse parity function. I know that, but I don't know what the support is. Let's say I have this a priori information. If you are to then do the completion in the next demonstration, then you should somehow look at the prior demonstration and figure out what the support is. Now, how would you do it? How would you look at this example and figure out what the support is? I mean, if you sat down for a while, just thought about things, and you will be able to figure it out, provided that there are sufficiently many demonstrations. But it's an algorithm that you would be doing. You would be sort of making up on the fly, but you would be implementing an algorithm in your mind. And the optimal algorithm, the information theoretically optimal algorithm, is known as the Gaussian elimination algorithm. So there's a way to do this optimally. I'm not saying that the transformer is doing it in an optimal way, but it has to be implementing some algorithm. And let me further clarify the formulation of ICL. So in a standard non-ICL learning, there's a fixed function that is being demonstrated. So X is the input, X is like the input image, Y is the label, and there's some true function that we are observing through the input-output relationship. And usually in supervised learning, the goal of training is to learn the function so that later on when you're providing a new picture, you can make a prediction as to whether it's a cat or a dog. But in in-context learning, it's a little bit different. In in-context learning, there are many different functions that can be demonstrated, and there are many different functions that are shown in the training data. And the goal of learning is to learn an algorithm. The goal is to learn not the function, but to learn an algorithm that can be used to determine which function f is being demonstrated. We want to learn an algorithm to be able to identify the support of the sparse parity function. So at inference time, once training is all done, then some function, some sparse parity function will be selected, and we'll see a bunch of demonstrations of it. And then we'll feed those demonstrations into the algorithm. The algorithm will identify which function is being demonstrated, if everything's perfect, and then it will make the prediction on the next input. So to analyze this in a scientific controlled way, we can, Garg et al. In 2022 proposed this stylized experimental framework. So we take a sequence model, they use a GPT, and I say GPT to specify the scale of this, but we can also use other sequence models like Mamba or RNNs. And so again, here's here's how we train directly for ICL. We initialize the GPT-2 model randomly, so there's no pre-training. We're going to train GPT-2 from scratch. We're not going to provide any text or language data. We'll just show a bunch of these in context learning data sets. So we'll sample a random function f. We'll generate n-1 in context demonstrations, and finally GPT-2 will be made to predict the nth label. So at xn is the final input that we provide, and the task of GPT-2 is to predict what the function evaluated at xn should output. So when we do this, well, what can these trained GPT-2 models do? Well, it can do sparse parity, and it also can do linear regression in a quite surprising manner. So let's say our function class is W transpose X, and let's say we just have we a priori know that these are the kind of functions that we get. Okay. And now let's say the model is shown n-1 in demonstrations, and let's say the demonstrations have no noise, so the function evaluation is exact. Well, so then this is the input data input sequence that's provided to the transformer. And what the transformer can do is it can look at these demonstrations, figure out what W is, and then predict W transpose X, Xn as a final output. But how would you do that? What's the optimal way to do this? Well, statistically, this is linear regression. So we know, us educated humans know that this should be solved with linear regression, set up some matrix, compute the inverse, the pseudo inverse or whatever. But it turns out the way transformers do it, if you use a depth K transformer, what it does is it sets up the linear regression objective function, initialize the W at 0, and then performs K steps of graded descent. This can be shown. It can be shown, proven that that algorithm is the minimizer of that loss when you train it in this manner. So this is a rare instance where people actually identify the specific algorithm that is being learned with in-context learning training. And it's very, I think, very cute, very impressive that we even know that, well, the depth of the transformer layer corresponds to the number of iterations that the transformer carries out.
So it's like it knows its own capacity.
Well, I mean, so if you kind of think about it, because transformers have no loops, right? So really, the number of layers is kind of the number of sort of computation steps that you can carry out. So I don't know if it knows its steps, but that's the best that it can do. 8 steps of computation.
And also maybe quite naive. So it says we find that the model is actually performing a K-step graded descent. That means when we observe what is happening in the system, there are some substructures that is somehow doing it, or it's more in a explicit way.
So a transformer is a sequence-to-sequence model. So every sort of at every layer, you get the input sequence is transformed to a different sequence. Now the input sequence, the numbers that are in after each layer can be it's not as is graded descent, but you can reinterpret it as being exactly graded. So every layer to probe it, you'll get numbers being transformed, and those are the graded descent values. Okay, so that's the sort of prior work on in-context learning, and I want to share with you one result that we put out recently. It's titled "Task Diversity Shortens the ICL Plateau." So what we'll consider is instead of a single in-context learning setup, we're going to consider what we call the multitask ICL setup. So we'll have, instead of having one task, we'll have multiple pools of tasks. So for example, linear regression is one task. Sparse parity is another task. There's some conjunction functions, disjunction functions, what we call quadratic regression. We have a sort of a collection of tasks, and within each task there are of course many So a sparse parity function would also you need to determine what's the support. So within each class, it's not a single function; it's a set of functions, and then we have a union of these different sets. So our main finding is that if we train on multiple different tasks, so that the transformer becomes capable of solving these multiple different ICL tasks, training becomes faster. So in these plots, we have sparse linear regression, conjunctions. This is sparse parity. And if we just train for just one single task, then this is the training loss max. There's a very long plateau, and then at some point, the transformer suddenly is able to it suddenly learns the algorithm, the one algorithm. And for parity, parity is actually a kind of difficult task to learn. So it turns out that we just we run it for 10,000, 1,000, a million iterations, and it just doesn't make any progress. But interestingly, so here we specify 6 different tasks. If we train the 6 tasks simultaneously, then for sparse linear regression, the plateau shrinks and we learn faster. For parity, we are now suddenly able to perform parity when we train on all 6 tasks. And this is counterintuitive because, well, if you have your transformer learn multiple tasks, in any reasonable statistical sort of framework, there'll be more information that you're learning. It sounds more difficult to learn more things simultaneously. But it turns out in this specific sense, if you train on more things, you actually learn faster. It's just so each iteration, there's no caveat. It's just each iteration is roughly the same amount of time. So it's a fair comparison. If you want to learn even if you only care about sparse linear regression, you shouldn't just train on sparse linear regression. You should train on all 6 tasks so that you can learn to do sparse linear regression faster. We observe a similar finding with state space models, which is a sort of competing sequence model that some people think will replace transformers. In any case, I don't know if that's going to happen, but with SSMs as well, we observe the same phenomenon.
When we're training on simultaneously on different tasks, and the loss function is also like weight among the tasks.
Yes, so we have 6 tasks, so there are 6 terms in the loss function, and we just use a uniform loss.
Yes, so if we have a really like fast convergence for that simultaneous training, does it necessarily means that for each task it improves better,
So
or
here,
it improves faster?
so here these are actually 2 curves. One is the test loss and one is the training loss, and they kind of just coincide. So it's hard to sort of tell them apart. But here the evaluation is only on sparse linear regression. So the dotted line, that's the evaluation, that's the test loss. So our mental model is in this scenario, we only care about sparse linear regression. I don't care about parity. But but I train together with parity and I learn to do sparse linear regression faster. Yes?
Let's say, like, is your intuition that this has more to do with like the way that it's learning, or like the way that it's, or like the tasks themselves that, I don't know, like, you have like sparse linear regression versus linear regression, and maybe this is tuning some sort of like regularization parameter.
So my high level honest answer is I don't know, but I'll sort of I have something to tell you. So I'll divulge everything that I know. Okay, so in the paper we do a lot of experiments to show that this is actually a very robust phenomenon. So the phenomenon is there. So then why is task diversity helpful? Why is training on many tasks make the training easier? Well, one thing that we did find, which is not a complete answer, but it's kind of a cute thing, is that we know what this plateau is. So the plateau is actually different from knowing nothing. Knowing nothing means just you randomly initialize a network, make some random prediction. That would be knowing nothing, right? But this loss, it's hard to tell, but it's a little bit below 1, and it's a little bit better than random guessing. So what it is what the plateau is. The plateau is what we call the optimal no context function. So imagine you want to you're given n-1 demonstration, and your goal is your job is to make the prediction on the last one. You ignore the demonstrations. You don't look at the demonstrations and just make the prediction. Now, this seems like you'd be making totally random guesses, but actually that's not the case because, for example, in this sparse parity case, depending on, or in some conjunction cases, the distribution of +1 answers and the -1 answers may not be 50-50. So if it turns out that because of the problem setup, 70% of the answers are +1, then this no context function learns to just predict the one that has a higher chance. So so we observed that the transformer learns this no context function very quickly, and then gets stuck there. So the difficulty is in somehow figuring out how to make use of the context that is being provided, and that would require an algorithm, and that algorithm is the hard thing to understand, and hard thing to apply. Now, in the interest of time, I'm not going to show you the evidence, supporting evidence, but here are the hypotheses that we lay out in the paper, and we provide some very incomplete evidence supporting it. So our experimental observations can be explained by these hypotheses. Hypothesis number one, there exists a common structure shared across these multiple in-context learning tasks. And number two, the plateau arises from the difficulty of learning this common structure. And number three, training on multiple tasks, they jointly, it makes it easier to learn this common structure. And very loosely speaking, maybe there's, so maybe there's this common feature that should be learned, and by observing multiple tasks, multiple uses of this feature, it becomes more easier to, you have multiple views of this feature that makes it easier to learn. I'm phrasing this in a very sort of loose and hand-waved way because that is the extent of our understanding. So that is to say, I really don't have a good understanding of precisely why this is happening. Okay, so let me conclude part 3 and also this talk. So in this work, in this paper, we identify that training on a diverse set of ICL tasks is actually surprisingly easier than training on a single one, in the sense that you get a more favorable optimization landscape. And let me now sort of distinguish the observation from things that we've seen in prior books. So the modern training of large language models, in that scale is considered one of the most important factors, right? With more scale, what people mean is use more data, you use a larger model, use more computation. Now, when you do things at scale, you use more data, and more data is statistically better. So that's good, and that's sort of at least intuitively well understood that more data is better. However, the blessing of dimensionality scale that we've reported this work is a bit different in that our observation is in the sense of optimization. LLMs are trained to do next token prediction, and this can be thought of as a very highly diverse multitask learning. When you do next token prediction, the text could be poems, it could be math problems, it could be news articles, and this is really a multitask learning problem. And when you scale things up and use a lot of more data, a lot of diverse data, then you get to use more data, and that's statistically good. But maybe there's another benefit to scale, and the benefit, and that being that when you scale things up and use a diverse set of data, maybe that furthermore makes the optimization, the training, also easier as well. And maybe that's partially explains the modern success of large language models. Thank you. Any questions? But yes.
I have a non-mathematical question. So nowadays, at least video games that I buy, they don't come with instruction manuals. It's you load it up and you go through it. So I don't even know how to ask this question, but with LLMs reinforcing classical reinforcement learning, can that be incorporated into such things where you tell the model to learn as if the video game is starting up?
Well, so nowadays video games don't come with instruction manuals, but they come with plenty of Reddit posts, right? So if you wanted to replicate that, you could just kind of crawl the web on, guides on how to play the games and you could do that. Also, I guess, so let me put it this way. So I think the main takeaway from that work is that using LLMs, you can make RL agents make some common sense decisions. So nowadays, people there's a lot of research on robotics and autonomous driving and people are trying to use large language models in decision making. So there's something in the street, and you need to decide: do you take the U-turn? Do you turn left? Do you honk your horn or something like that? And this high-level decision making is now people are trying to delegate this to a large language model, and it can make, in many cases, not always, but good common sense decisions. Yes.
The general structure that you said that the LLM is able to learn. You need to refer that. You think it's learning an algorithm or is it learning something even more general? Does it even more capacity than just learning an algorithm like the previous program? Sure.
I don't know. I mean, well, first of all, the language model has to learn this sort of in context framing. That has to be done because yeah, I mean, not all tasks are sequence tasks are in context framing things. It has to learn that, but I'm not really quite sure what the commonality between quadratic regression and sparse parity is. So, but in the paper, we do experiments on completely unrelated, what we think are completely unrelated tasks, and then they don't really affect each other. So the tasks have to be different, otherwise there's no diversity, but if they're just completely disjoint, then they don't interact, they don't help each other. No, yeah.
Do you think like a possibility is that there's kind of like the multiple tasks kind of like create like slight like fluctuations in the other ones that help them avoid like local minimums? That could be a possibility. Like,
So I'm not sure if I don't know if there are local minimums. So my operating sort of intuition in deep learning training is that there actually are no local minimums. I don't have any. I have my reasons to believe this, but I don't have a very strong evidence for it. But here things seem to get stuck, right? But it could be because it's stuck in a local minimum, or it could be because the landscape itself has a very long plateau. So, and I think it's not a local minimum because in these plots you see that it takes a long time, but it does escape. So if it's if we're trapped in a local minima in the sample pass training, maybe it shouldn't escape. So maybe it's this very flat plateau that is slowly, sluggishly traversing and then reaching the end. I got it.
and then maybe like the other things, there could be like pushing it to escape that plateau.
Maybe. So my guess is that the landscape itself becomes much less plateauish. So in the language of like saddle points, maybe there's a more sort of steeper escape direction. But I'm not quite sure. And it's so if there is a good way to set up an experiment to measure that, or if there's a good way to set up a toy model to be able to prove that, that'll be very good promise. It's
I have maybe an unusual observation, which is, so I'm not a mathematician, but this sort of experimental work makes me think that computer scientists and mathematicians are much more like ecologists and zoologists, where you've dug up some deep sea creature from the bottom of the ocean and it looks a lot like other things, but it's not quite the same, and you're probing it in these experimental ways that are very different from things that have come in the past, right? Like this is a whole new realm of sort of experimentation that I can't think of an analogous problem space. Right.
So that's why I use the phrase "a science of large language models." Some people have used the phrase "physics of large language models."
Yeah.
And when they say physics, they don't mean using tools of physics, but more the scientific controlled experiment methodology. And yes, I do think of LLMs as this alien created life form that I'm trying to understand.
Yeah.
Yeah.
For multitask training or LLM, like you mentioned that when we are well, we're trying to train it by like linear regression problem, and when it's successfully trained, we see that there is some something like gradient descent happening there. So is it generalizable to many simple tasks in the sense that when we are trying to training the LLM for some different kinds of simple tasks, we can always observe some some structures or some processes within the large language model that is actually performing some algorithm that is already developed by human to solve those simple problems.
So, okay, so this prior work, which identifies that transformers are implementing gradient descent. It's more of an exception. So this is the only instance where it's known or there's some theoretical understanding as to what algorithm is being internally implemented. In all other cases, and I've tried looking into it a little bit, and did some probing, I can't figure out what algorithm the transformer is implementing. I don't think it's implementing the optimal algorithm. I mean, in this case as well, I mean, gradient descent is not optimal, but it's because it's not accelerated. Okay, so in the parity task, in the sparse parity task, the optimal algorithm is this Gaussian elimination thing, and that feels like a very unnatural thing for transformers to do. And when I take a look at probe things, I don't think the transformer is implementing Gaussian elimination. I don't know what it's implementing, but I don't think it's Gaussian elimination. So if anybody can find another setting in which we can identify what it is that the transformer learns to implement, that would be a very good progress.
So that the gradient thing is kind of a special case that we found.
It's the special case. It's the only case that we figured out. Okay, if there are no other questions, thank you, everybody.
Thank you.
Yeah, so Stan was able to get Stan to move. So there was a sequence of things where first it was decided that office that Stan is in now would be there for him. This was actually several years ago now. Several years. And then it was